So invariant points and lines are to do with matrix transformations and linear transformations. And they don't come up very much in the textbook. So unfortunately, this is just, if something that you're trying to look for practice, the best place to find this practice will be from the slides that I've got here, because I've tried to grab as many of the questions as we can. They will probably be scattered throughout the rest of the booklet as well. And the word invariant, what does the word invariant mean? Doesn't change, okay? So it's pretty obvious what we think we mean by invariant points and lines. So an invariant point is one which is unaffected by a transformation. So you could have a particular coordinate, you could transform all of space, so you're imagining back to those videos of all of the grid completely shifting and changing, and that point after the transformation will not have moved, okay? If you imagine giving all the different points different colors, maybe all of the other coloured points have shifted around, but one of the points where it was is in exactly the same place. Can you think of, before we even think about the rest of this bit here, can you think of an invariant point that you should be able to tell me about for a linear transformation? Origin. The origin, okay? So the origin is always an invariant point in a linear transformation, and that came back to our definition of what we said about linear transformations. So the origin will never move under any transformation. The next bit gets a little bit more complicated, okay? It says an invariant line is when each point on the line transformed to give another point on the same line. Now, this is where things can potentially be a little bit interesting. I'm going to just actually add in another slide here for a second just to do a quick bit of a drawing. Now, an invariant point is one that, let's do these with my black axes to begin with. So this is for an invariant point. Where that point there stays exactly as that point, but maybe this red point has moved down here, or maybe this yellow point up here has gone somewhere over here. We don't really know what the transformation is, but we can see from this bit, obviously, this is the invariant point. Now, there's a couple of different ways that we can think about an invariant line, okay? An invariant line could be something that looks like this. It could be something where this blue point goes to this blue point, where then this purple point goes to this purple point, and where this green point goes to this green point. And in fact, any point that is along this line will be mapped to the exact same point on there. So this particular type of invariant line is a line made up of invariant points. Good. So you can have one which is like a line that's made up of invariant points. So yeah, the line isn't going to change, but really it's just made up of lots of points that haven't changed. If we go back to what our definition here says, it says an invariant line is when each point on the line transformed to give another point on the same line. So what could the other version be of an invariant line? What might be different about a second way you could have an invariant line? Yeah, the points don't necessarily have to be in the same point as long as they lie on the same line. So as long as they transform to give another point on the same line, not necessarily the same point on the same line, but another point on the same line. So yeah, one of the things that could have happened is instead of this blue, purple, green, it could have gone blue, purple, green down on the other side. Or it could have gone blue up here, purple down here, green. I mean, I can't think of a matrix transformation would do that, but they don't have to land in the same place, okay? When they land in the same place, these will have exactly the same coordinates. When they don't land in the same place, which maybe I should just quickly draw what that might look like. So we've got this going to this. So what did we have? We might have the blue one going down here, the purple one might actually be in the same place, and the green one might somehow get mapped to this. So we'd still have an invariant line, but this time they don't have the same coordinates, but they do have the same relationship to the line, if that makes sense. They'll still have, I don't know if it's y equals 2x, the y coordinate will be double the x coordinate. Okay, and this is probably the more challenging types of questions that we come across here, but actually the practicalities of solving some of these things isn't quite as complicated. But I want that idea of what this is, of going on behind these questions to sort of make a bit more sense before we look at this. Okay, so let's actually look at the rest of what the notes are that we've got written here. So I've got two particular examples. We've got this particular transformation, and this transformation of 0, 1, 1, 0 is a reflection in the line y equals x. Can you just remind me, though, how would we work out what this transformation actually represented by drawing something? So this is what I hat was previously, but now we've got it as 0, 1, so it's now become like that. And obviously j hat is usually like this, but it's now become 1, 0. So it looks like that. So you can see that we've got a reflection in the line y equals x. I know it obviously tells us that on the page, but it's just good to remind us of this. So the invariant lines that we've got here would be the line y equals x, because that's not going to make any kind of difference at all that we've got there. And then if you think about it, any line that has a gradient of -1, if you reflect any line with a gradient of -1, that line, this section is just going to flip over to that side, and this section is just going to flip over to that side. Excellent, yeah. So the second invariant line here is perpendicular to the mirror line. And it's got a plus k here because it is any line perpendicular.
So it could be anywhere along that line?
It could be anywhere, yeah. I might actually draw another one on. So it could be like this, or it could be like this. Obviously, hopefully they're drawn perpendicular. Yeah, they are. Because if you imagine it, any of those lines, when they flip, they're going to be in the same kind of place, okay? And so some of these, if you're going to try and find an invariant line or an invariant point, some of them are thinking like logically or reasonably about what does it mean? If they said you've got this kind of matrix, find out the invariant lines, where you'll go like, okay, well, it looks like a simple matrix. So I'm just going to think about what the transformation is, and then I'm going to think about what lines don't move. And there's not necessarily tricks to that. It's just about trying to think to yourself, okay, well, if all of space is flipping, what are the bits that would be staying the same? And building up what that invariant line or things would look like, okay? What about the invariant points that we have here? What would be the invariant points for this first one that we've got? Which points would not change?
One of the right left.
Good. So the invariant points lie, it's a shame I can't write down properly, lie on y equals x. The invariant points lie on y equals x, because if you imagine any of these points along here, you do a reflection, and you get the same point. So can you give me an example of a coordinate that doesn't vary? 2, 2, 3, 3, pi, pi, 8, 8, whatever. Anything where the x and y coordinate is the same, it wouldn't vary. And we'll examine in just a second about like what we can do with algebra that shows that. This second one that we've got here, we recognize this matrix. This matrix that I remember some people were like, oh, I need to memorize that one. I actually checked. This one is in the formula book if in a moment of panic you can't remember what the rotation matrix is. And there are no invariant lines here. Because if you think about any of the lines to begin with, if they rotate a bit, they're not going to be in the same place. But it does say here unless theta is 180 degrees. But then it's just becoming a rotation. If it's 180 degrees, you'd think about what ones you might have there. Any straight line through the origin would be invariant if you rotated it 180 degrees. And the only invariant point is 0, 0, okay? So I'm going to just quickly come back to this other page here, and we're going to look at that reflection matrix again and just see if we can confirm some of those ideas. So the reflection matrix that we had, sorry, I didn't give you enough space to do this, but it was 0, 1, 1, 0, yeah? Now, if I wanted to find an invariant point, if I applied this transformation to a coordinate, x, y, what do you think the result would be if I want to find out a point where it doesn't change at all? It's just going to be xy. If I'm transforming a coordinate, xy, and I want it to not vary, if I want it to be invariant, it should just give me xy. You don't have to necessarily write this bit down because this is some ideas that's going to help us to do the next question that we've got. So this is what we're saying. This does not vary to give us this. So let's actually just come back to this. Let's work out what does this left bit actually work out as. It just comes out as yx. So we get yx equals xy. Exactly, because you know with matrices we can compare the top elements and we can compare the bottom elements. So when you compare the top elements, you get y equals x. When you compare the bottom elements, you get x equals y. So it's just telling you if x and y are equal to each other, then these things would be equal to each other. Therefore, there would be no varying that would be happening there. Okay? So those ones are a little bit more complicated, and we're about to have a look at an example that should help us to do that kind of thing. Okay. So the one I wanted to look at was, and this, prepare yourself because this is quite a challenging question, and I couldn't find another question like it anywhere, so I've made one up that's basically the same but with just different numbers. So here we have, it says a matrix P represents a linear transformation T of the plane. And it says to describe the invariant points of the transformation and then to describe the invariant lines of the transformation. So you look at the matrix, and this matrix does not seem to be doing anything that looks like, oh, it's just a reflection. So I know what the lines would be, and I can just make it make sense in my head. This one's definitely a bit more complicated looking, and I'm going to start off by showing you like an animation of what this one looks like. So it is this one. Is it 3, 3, 4, 7? Yeah. Okay. So here, this is what original space looks like, A and B, like I hat and J hat. And remember, we've now said that space is being warped so that the I hat is looking like that, and the J hat is looking like that. So this is what space was, that kind of A and B, and it's now imagining that those two things, they're kind of like squashing and stretching, which is why you can see all of these lines here, which are in the central part of the circle, they're all evenly spaced, aren't they? They're like evenly spaced like time around a clock, like the hours around a clock. And you can see that they're much more densely packed over here and more densely packed over here because A and B have kind of squeezed together and stretched outwards. If you kind of imagine what that might have looked like in the animation, all of space is kind of stretched out in that direction, which is why these lines are more densely packed here. So what do you think we might look at to try and figure out what the invariant lines are? And I'm just talking about the geometry here. I'm not talking about like any of the algebra. What might we look at on the diagram that seems to show an invariant line? What do you think these purple lines here might be helping us? How could we use those to help us see which ones are not varying? Okay, so for example, this blue line that I've got here, this is it in the old space. The blue line means before the transformation. So before the transformation, the blue line was like this. The red line is after the transformation. Exactly. So the red lines and blue lines, if they line up, it means that they haven't varied. I'm sorry, I should have said at the beginning, the blue was before the transformation, the red was after the transformation. So roughly, can anybody give me like a rough idea of what they think an equation might be of one of the invariant lines?
Y equals 2x.
Yeah, something, probably something like y equals 2x, something that's kind of going like this, because maybe in between here and here, we're going to have something that looks like it's just going to be going all the way through in both directions. There's going to be another invariant line as well, and it's going to be something else that's going to pop up in a second that we'll see, and then we'll try and look back on the diagram and see what works.
Is one of them x equals 0? Just the axis and spread?
That just happens to be, I think, the axis. Well, actually, I'm not sure what it will be. We'll go through the calculation, but it won't be x equals 0. That isn't one that we have here, but you'll see in just a moment. Okay, so first of all, we're going to describe the invariant points of the transformation. So one of the invariant points is just going to be, let's not forget about the origin, because we know that the origin is invariant. And this question is quite long, so if you don't mind writing relatively small here, just to make sure you can fit it all on the page. The next page I've done bigger so that you can do your own working out a bit longer. Okay, so because it's invariant, we know that if you do 3, 3, 4, 7, and if you apply it to an x, y coordinate, you should just get xy. So what does the left-hand side of the matrix come out to be? What's the first part?
3x.
So you get 3x plus 3y and 4x plus 7y is equal to xy. So just as before, these bits must be equal and these bits must be equal. So I get 3x plus 3y is equal to x. And if I try and solve that equation and find out what y is equal to, well, I get 3y is equal to minus 2x. So y equals minus 2/3 x. And then from the green part, I get 4x plus 7y equals y. So when I subtract y and subtract 4x, I get 6y equals minus 4x, or y equals minus 2/3 x. So what's that telling me? That doesn't seem to have told me an invariant point, does it? So what are the invariant points? Now that we know the origin is invariant, but what other things are invariant here?
That line.
Yeah, any point on the line y equals minus 2 over 3x is invariant. So I didn't even really need to say 0, 0, because 0, 0 is going to be on that line, isn't it? So I should say here, all points on the line y equals minus 2 over 3x are invariant. But that's weird because when I come back here, minus 2 over 3x, I don't really see it doing like anything on the diagram. But minus 2 over 3x, let's just quickly think why that would be. So, I don't know, if x was 1, it would be, what am I talking about, 3 and 2. Yeah, it's kind of like this sort of line here. Actually, is it this kind of line? Looks like it's going to be somewhere in between here. There's going to be some space that isn't being bent around at all, but it's just kind of difficult to see because of the way that that wheel is. But it definitely is invariant because we could put those coordinates in and see that nothing would change. But it doesn't seem to have given us the one that we predicted that we thought was going to be somewhere along here, which we're going to try and find out now where that one comes from. So it seems like this line that we're talking about that's along here is probably going to be perpendicular, but out of these different scenarios that we've got here, is it this one or is it going to be this one? It's going to be the bottom one. The one that we could see on the diagram is going to be where all of the points that were there are going to be shifting. And actually, if we go back to this, we can probably have predicted that anyway, because any of the coordinates that would have been along that line are being stretched out, so they're going to be stretched out further away from the origin. So it doesn't make sense. That one was never going to be an invariant line made up of invariant points. It's going to be an invariant line where all the points are getting scaled up and shot further along that line. And this is where the algebra becomes quite difficult about what we're going to do next. So I'd say this is going to be the most important part of the bit here that we're going to listen to, okay? So for part B of the question, it wants us to describe the invariant lines of this transformation. Now, we already know, because it says the invariant lines, we already know one of the invariant lines, don't we? So we can say y equals minus 2 over 3x is an invariant line. Okay, and now we're going to try and say, let's make the most general invariant line that you could possibly have, and it's going to be a y equals mx plus c. It's going to be an invariant line that we could have here. And we have to have that plus c in there, just in case there's going to be something where actually the whole line is invariant. And we're going to see if that, we're going to see what happens. So, we want to see what happens to 3, 3, 4, 7, applying to x, y. I'm going to write that down in a second. Now, instead of writing down x, y, if I just write down x, y, and then I get x, y again, I'm stuck back in this previous thing here. So what could I write instead of y? No, I already know that minus 2 over 3x is one of them. I'm wanting to keep it as general as possible. So I'm going to say my y value is just mx plus c. So we've still got this relationship between the x coordinate and the y coordinate. They've just come from y equals mx plus c. Now, if I wrote down this, am I describing that scenario where the points could move to a different point on the line? I'm describing, again, an invariant point, giving you the exact same invariant point. So I need to make an adjustment. I cannot use the same letter here as I did over here. Let me just say that one more time because it's quite important. If I just left it as x here and x here, then that's just saying I'm going to go from the coordinate x, mx plus c, and I'm just going to go to the same coordinate x, mx plus c, and I've got it just as an invariant point. but I need it to be an invariant line. However, I still need the bottom part of the coordinate to be the top part of the coordinate multiplied by m and c added onto it. So we could change the letter and just call it D, E, whatever we wanted to call it, or what you'll probably come across if you see this in a mark scheme is they just call it X dash and X dash. So now we have got that it's going from a coordinate to a new coordinate that still has the same relationship. And yeah, X dash is fine for us to use, but so it is a new coordinate because X has gone to X dash, but same relationship. And if it's the same relationship, it must be the same line, because that's all a line is. It's just a relationship between 2 points here. For the last 2 years I've done this topic, both classes have found this like really confusing. So the fact you're like with this, they were like off the wagon by this point here. So you're doing really well if you understand what's going on so far. But it's going to get a little bit more spicy now. So we're actually now going to do some maths with all of this stuff, right? Left-hand side, we know what it's going to expand to. Well, not expand to. Yeah, I guess you call them expanding these matrices. So I've got 3x plus 3 mx plus c. Those bits multiplying. And I'm just going to go a little bit quicker than I did before to save me a bit of time. What's that equal to? No, it's just the top parts is all I'm saying. So it's just equal to x dash. Okay? Now the bottom bit, I've got 4. I'm going to leave a little bit of space there for me in just a second. So I've got 4x plus 7 mx plus c is equal to m x dash plus c. What do you think we've got here? We've got simultaneous equations, okay? And for this simultaneous equation that we've got here, we're going to take x dash and we're going to substitute it into the second one. Because x dash is the thing we don't want. We want our whole thing to be in terms of x, m, and c. And then we're going to try and see what we're going to do with this. So I'm going to put that whole thing in there. And what I'm going to do is just tidy it up a little bit. So I have, just by expanding it, 3x plus 3mx plus 3c, and I'm going to put that in here. So if you have run out of space, you can always go on to the next page on the bottom half. There's a bit of gap there that you might do, because this is important to get this bit done so that you've got it in your notes. On reflection, I probably should have given you more space for this one than the second one, but I thought you'd need space for it, okay? So I'm going to substitute this in here. So I've got 4x, and I'm going to expand the brackets, plus 7mx plus 7c equals m lots of this thing that I've got here, which is 3x plus 3mx plus 3c plus c. So I'm just going to keep going now. Let me know if I've gone too fast, because I want you to be like making sure you understand what's happening here as well. So I have 4x plus 7mx plus 7c equals 3mx. I always try and write it in the same order. Plus 3m squared x plus 3cm plus c. So it looks kind of like we've got a few common kinds of things that we might be able to do here. if in doubt with an equation that's got lots of variables, what could I possibly do? Move some stuff around. What should I make it equal to? 0. Yeah, 0 is probably going to be something here, because you can start to see maybe there's a kind of quadratic in here, and if it's 0, we at least know a few tricks of some things that we can do with 0. So I'm going to say 0 here, and I've got, let's start off with this term that I've got here. So I'm gonna write and underline it when I've dealt with it. So I've got 3m squared x. Okay, so then I've got this one here. I've got 3mx and plus 7mx minus 4mx. And then I've got a 3cm, which I'll write next. And then I've got a c minus 7c minus 6c, and then I've got minus 4x. Now, you might not know what to do here, so I might just tell you what we're going to do here. We've got 3 terms that are to do with x. If I factorized x from these 3 terms here, I get a quadratic with m, and then I get something left over, and then we're at least in a stage where we might be able to solve it. So well done for keeping going here. So I'm going to factorize out the x, and we get 3m squared minus 4m minus 4. That's from this term, and this term. And then what I've got left is plus 3cm minus 6c. But what can I do with 3cm and 6c rather than writing? I can factorize those as well. So what can I take out as the highest common factor? Higher? 3c. So I've got plus 3c m minus 2. We're really nearly there, guys. This is a very demanding question, and I want to show you the hardest questions so that you don't get stumped in the exam. It's not fair for me to make the lessons easy and then the exam's hard. Right, tell me about that first quadratic that we've got there. How can I factorize that first quadratic, please? Shall I give you a clue? One of the clues is there's something here. It's going to be here. And also, what does this bit have anything to do with? What would the value of m be? Remember we predicted that the gradient was going to be 2? I know you wouldn't have access to that in the exam, but m minus 2 is one of them. Which means the other one is? Okay. Now there's a lot of truth that you're going to see here. You're suddenly going to go like, oh. There's lots of things that are going to connect back to what we've done here. So I want this entire thing to be equal to 0. That's what I'm trying to solve when I'm solving this equation. So this thing is equal to 0 when what is true? What value does m have to be? Not m is 0. I want the whole thing to be 0 to make it equal to 0. What could you say about these things here? Good. So if m is equal to 2, then equation is correct. Do go on to the next page if you need to. Now, if m is equal to 2, what's the value of c? Does it matter what the value of c is? No, because as long as m is 2, I don't care what this value of c is. So if m is equal to 2, the equation is correct, but c can take any value. what else looks like we might be able to make this equation equal 0? Could you tell me a different value that m could be that would make the equation, and a different value of c that might make the equation equal 0? You could make c equal 0, and you could make m equal minus 2/3. And what does that correspond to, Sam? It's the same equation that we had before. M is minus 2/3 and c is 0. So it all comes out in this equation that we've got down here. It's kind of cool, isn't it? So the other one is if m equals minus 2/3 and c equals 0, equation is correct. So I've sort of run out of space. So our invariant lines are y equals minus 2/3x and y equals 2x plus c. So although it's difficult to see in this bit, we can obviously see that y equals 2x looks like it's going to be in the invariant line that we've got there. This is a form of y equals 2x. And we've also got this one, which is the version of minus 2/3x. Those are our two invariant lines that we've got. Also, though, if it was y equals 2x plus 5 or y equals 2x minus 3, those are also going to be invariant lines as well. Well done, because that is, I think, one of the most challenging questions that you'll come across. Obviously, you might have come across that in the exam without me having done it in class, but I want to show you things that are weird and different, because maths isn't always just about following a particular method. You got down to this bit here and you think, okay, let's try and work out what's true. So even if you never come across this in a formal assessment, this is interesting in itself, especially when you got these things at the end and you're like, oh, minus 2, 3, and 0. Yeah, we've already done that one. That's already been there. So you've got all of that working out. I'm going to leave this on the board here. There's another question that I've made up that's exactly the same method. I've just changed the value of the matrix. See how much of it you can do without looking at your notes. If you need to, you can glance at the board and see how that goes there, okay? Well done.